All right, last little page of notes there for this 2C assignment. Okay, here's how the AP test will use the quotient rule. We've got a table here with some information about a function f, its derivative f prime, a function g, and its derivative g prime. When x is -1, we have these values. When x is 0, we've got these values. So the question is, find h prime if h of x equals f of x over g of x. Well, using our quotient rule, we know h prime of x is derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. G of x squared. Okay? Well, we want to find h prime of 0. So we're going to have all of that with a 0 into it there. G of 0 minus f of 0, g prime of 0, all over. I'm going to write this a little differently. G of 0 squared. Well, what are these values? Let's go to our table here. So f prime of 0 is -3. So we have -3. G of 0 is right here, 5. Minus f of 0, 2. And then we have g prime of 0. That is -1. All over g of 0 squared. G of 0 is 5. So that'd be 5 squared. So on top we have -15, and this would be a +3. -15 plus 3 is -12 over 5 squared, 25. All right. How about if h prime of -1? Find h prime -1. Well, here we have a product function, okay? And so we can do this a couple ways. Let's think of it first of all like that, okay? So h prime of x is derivative of the first. Well, there's our first, which is 1, times the second, f of x, times g of x, plus the first, which is x, times the derivative of the second. Well, we'll have to think about that in our next step. Derivative of f of x, g of x. That guy is going to need the product rule. So h prime of x is f of x, g of x, plus, okay, quotient rule here, product rule. Derivative of the first, f prime of x, times the second, plus the first times the derivative of the second. Watch out, I almost forgot this little x times out here. Okay, so all of that with an x out here. Now if I distribute that x, I'm going to end up with this. I got f of x, really a 1 times, so I'm going to put that there for a moment, g of x, plus x times f prime of x times g of x, plus, distributing this x here, x times f of x times g prime of x. Now, look at this. We had three factors multiplied to start. In the end, this is kind of like a 3-factor product rule. What did we end up with? We ended up with the derivative of the first, 1, times the second times the third, plus the derivative of the second thing times the first and third, plus the derivative of the third thing times the first and the second. So if you understand that, in the future, we can just take that straight down to here. It's kind of a three-factor product rule. So now when we got h prime of negative 1, that's what we were looking for. We got 1 times f of negative 1 times g of negative 1 plus negative 1 for x, f prime of negative 1, g of negative 1 plus negative 1 times f of negative 1 times g prime of negative 1. And now it's just a matter of using our table to read all these things. Negative 1 is that top row. So f of negative 1 is going to be 4, nope, 3. G of negative 1 is negative 2. And then we have negative 1. F prime of negative 1 is 4. G of negative 1 is 2. And then we have negative 1 that was already in there. F of negative 1 again is 3. G prime of negative 1 is 2. Now I think I skipped this one here. This was G. This is supposed to be negative 2 here. All right, I think I got that right there. I copied all those right. So that ends up being, what do we got here? We got negative 6. Then we have minus 8 and minus 6. So that looks like negative 20. All right, that's the idea there. Okay. Now, one more little thing. We got some higher derivatives. And what a higher derivative means is we're taking a derivative multiple times here, all right? So we have things called second derivatives and third derivatives and fourth derivatives. And all that means is that we're going to just repeat this derivative process. So here's a question. We want to find the second derivative of s of t, which is the position function for a falling object on the moon. So here's an equation from the moon. Compliments of our NASA peoples. And so if we want to find s prime, well, we know how to take that derivative. Just drop that 2 down using the power rule. 2 times 0.81 is 1.62 t, and the derivative of 2 is 0. If we want to find the second derivative, we write that like this. That is the derivative of the derivative. Well, this is negative 1.62 t to the first, so that, since this is t to the first, using the power rule, negative 1.62. That's the second derivative. Now, in Leibniz notations, that's Newton's notation there with that little x, the little apostrophe. We say this: the derivative of s of t is negative 1.62 t. Now, that's a derivative of s of t. Or sometimes we'll say this, that is ds dt. Now, if we want the derivative of the derivative, we write that like this. The derivative of that's an x. It should be a t. Okay? T, because our variable is t. And this should be x. All right, so let's talk dt. Same idea. Well, this notation, it kind of is multiplication, kind of isn't, but we write this like this. If we were to think of these as variables, we have like a d times d, that's like a d squared, s all over, and then we write it like this, dt squared. Really, technically, it should be like this, but our notation we write is like this. Okay, this means the second derivative. So that just means the derivative of the derivative, and that is negative 1.62 in this case. So the second derivative written as d2 s dt squared there, okay? We just say the second derivative is also written like this, okay? Now, when we're talking about motion, things in motion here, in physics, we often use s as the position function. This is the position of a point or position of an object. If we take the derivative of position, we have the change in position with respect to time. The change in position with respect to time is velocity, how much the position is changing, how quickly. Okay. Now, if we take the derivative of velocity, we get acceleration. The change in velocity is acceleration. You might be familiar with that from physics. So the second derivative, if we start at the position, and we take the derivative and take the derivative, that means that the acceleration is the second derivative of position. It takes two derivatives to get from position to acceleration. So that's an important connection we'll use a whole lot as time goes on here. So here's some notation. First, second, third, fourth derivative, we write like this: y prime, y double prime, y triple prime. Or we put this little number in parentheses. It's not y to the fourth power, it's the fourth derivative or the nth derivative. Okay, sometimes we write it like this with the x. In Leibniz notation, we can write it like this: dy dx. Second derivative, d2y dx2. Okay, third derivative, fourth derivative, so on and so forth. Or we can write it like this for a function f of x. Or sometimes we use this big D notation, and that is the first derivative of y with respect to x, first derivative of a second derivative of y with respect to x, so on and so forth. Again, not a power, it's a derivative, meaning we're repeating the derivative process over and over again. All right, well, there's a few things there. Hope that helps, and keep working hard on those product and quotient rules.